talk is about performance of fire resistance heated energy storage for industrial heat applications and round-trip electricity storage.
Thank you.
Oh, sorry. All right. So first principle study on thermodynamic stability of uranium dioxide with its gas incorporation via alpha decay.
No problem. All right. Good morning, people. I'm basically working on the first principles. So I want to talk about the recent work on the advancement of the first principles, and then why we have to utilize first principle calculations to understand the material properties. So the example I brought here is that thermodynamic stability of uo2 with helium gas incorporation by alpha decay from uranium into thoriums. I know that MIT will launch this September about AI department, AI ecology. Nowadays, the machine learning is kind of hot topic in over the computational society. That because machine learning can materialize or realize artificial intelligence by using deep learning technology. So basically, using this technology, we are going to simulate our brains in the make a decision of something. I'm working on actually this kind of things these days. But I think machine learning and artificial intelligence can mean a lot of things. But in the science or engineering field, we have to really focus on that. We have to analyze big databases and apply machine learning to find out key descriptors. For example, we have certainly a certain database. This can be like really measured from experimental work or modeling or simulations. And then we have a lot of database to achieve something or to develop specific material like a silicon carbide. But if we have all like the same objective, this database cannot be random. They have a very strong, highly correlated correlation actually. If you apply machine learning technology to these databases, machine learning computer can propose us certainly the very strong correlations for the desired performance, the single maybe variable descriptor. Once you identify the key descriptors, you can optimize on a single descriptor to achieve your targets. This is the power of the machine learning technology. I think this is a strictly mean of the applicable to science and engineering field. Everybody else is very, confusing. Many algorithms applicable to electronic department to do, the driving or something. But I think in the machine learning technology, in the material science point of view, is this one actually. But the problem here is that the database, the data quality of database can be different from MIT or Stanford, Harvard, or in certain unknown college or center. So the achievement of secure of this database environment is very important. So in this point of view, I applied first principle calculation to achieve the highest reliability and accuracy actually. The first principle is the quantum mechanics basically. It is not based on any empirical assumptions. Even Elon Musk, he mentioned that one of the key sources of the success in the business is first principles. Don't follow other people's advice or trend. You have to think about really fundamental ground to be successful. So here we try to rely on our regions. In modern science, the first principle calculation is the quantum mechanics, how to solve Schrödinger equations. But we have 3 Nobel laureates who developed computational or numerical methodology to solve Schrödinger equation using supercomputers. Now you know that we have very advanced supercomputer technology, and also we have very good software engineering. Nowadays, who can defeat, computers in the, Go games? We cannot defeat it. We have very advanced ones. So why don't you use this first principle calculation to acquire certainly highly reliable database? Basically, if you apply Schrödinger equation to certain material, you can apply every kind of material properties. You want to utilize it. And this material properties outcome can be directly compared to experimental observation. So you can validate your calculations actually. In my group is working on the basically many fields. I'm mostly working on the renewable energy sector, fuel cells and lithium-ion batteries. But I got a PhD from Pourbaix in MIT Material Science Department. Lithium-ion battery and solar cells. And some part of my research work is about nuclear energy, especially on pyroprocessing and fuel recyclings at that targets. And I'm going to show the example of my work on this field. Okay. So conventionally, we believe in that in material science department, we believe the tetrahedrons, structure, property, processing, and performance, they are so deeply interrelated, correlated. So accurate characterization of these things are very important in the database. Let me show you that how to achieve the highest accuracy or reliability of this property using first-person calculations. Structure prediction in the under vacuum condition is well known actually. You can apply energy convexhull theory, Ab-initio thermodynamics. For example, platinum iron alloys as a function of ion compositions, you can predict very accurately the ground state structure over the compositional space, very accurately. You can easily calculate so many different structures, and you can apply Ab-initio thermodynamics. You can find out the ground state structure like that by minimizing the chemical potential. This was actually, computers predict that iron platinums, they form core shell, layer by layer, iron, platinum, like that. But actually, this structure was actually experimentally validated. So we are so sure about that, the accuracy of our database. Or another one, aluminum nitride is key material in the display materials. We could calculate the structure, the powder structure, not the atom structure, powder structures. And the experimental validations was really well done by our predictions. And we published in the CABA. Also, you can apply first-person calculation structure prediction theory to the multi-component alloys, copper, titanium, and the gamma alumina. This was done by to improve copper electric conductivity and the tensile strength together at the same time. This is conventional law. Without titanium, you cannot get over this conventional, inversely proportional conventional law. But if you apply trace amount of titanium into the alumina, you can get over easily this performance. So this is the best one in the world so far. We achieved that. Oh, but how about hybrid interface? You can still very accurately capture the structure between amorphous interface and amorphous and the crystalline interfaces. We found out that this structure was actually correctly predicted by computations. Computation told us that if you mix the phosphorus sulfide and cobalt phosphorus, they form coaxial structure, and the surface is going to be the amorphous. This material actually was known that very good material for hydrogen generation, actually. We published in the several prestigious journals. How about the structure prediction is an aqueous solution? It's more interesting in the nuclear industries. We can apply actually grand canonical potential concept to, for example, some particle or metal in the aqueous solutions. If you utilize that algorithm, you can also calculate energy convexhulls, as a function of oxygen chemical potential. This is the picture predicted by computation, first-person computations about platinum nanoparticle structure in the acidic solutions. Very low chemical potential of oxygen, platinum metal is stable. But if you crank up oxygen chemical potential a little bit, on the surface of platinum, they absorb hydroxyl group first by split of water. And then oxygen come up, and even the oxygen go into the surface space of platinum nanoparticles. This is amazing why platinum can be rust. You know, platinum used for wedding ring. They believe never rust, but actually in nanoparticle platinum, they rust. How about electrochemical properties? Even first-person calculations can predict Cyclic Voltammogram on the basis of a completely pure database of first-person calculations. Here, you can know exactly the structure, and we know how much of the proton and electron has to transfer to form these structures. In this case, then if you apply this theory, current density under the capacitors and the time variation of voltage, you can find out the peak. Whenever there is a electrochemical reactions, you can see that peak here like that. Then you can give this data to the experimental measurement, and then you can validate the database. How about electrochemical stability? We believe in that platinum particles very inert to the solution, but this picture shows that platinum nanoparticle of this size range can dissolve in acidic solutions by Pourbaix diagrams. You know, Pourbaix diagram is only available for bulk pure materials. No Pourbaix diagram for nanoparticle. But this is the first time we calculated Pourbaix diagram of platinum nanoparticles and shows that 1-2 nanometer platinum nanoparticle can dissolve 0.6 volt. But bulk particle dissolve only 1.0 volt with respect to standard hydrogen electrode. So nanoparticle is kind of dangerous to utilize in certain applications. The stability is not secured anymore. This is the design concept. I mean, using the possible calculations, can you improve stability? You can do. We can encapsulate the material by very thin layer of carbon, maybe or graphene. This is very way to control interaction between the water or oxygen with the core metals. And also you can block dissolution of this metal into those active solutions. This is, I think, the design principle you can utilize from first principle calculations, actually. How to wrap up? You can do like that. We found out that graphene fragment with a doped nitrogen, 5% of nitrogen dopings, actually they made by themselves for wrapping up the nanoparticles. This is a good way to do design of encapsulated nanoparticles. Can you calculate free energy diagram for any reactions? You can do. As a function of, especially here, electrochemical environment, you can calculate Gibbs free energy of certain, here the oxygen into final product, H2O, by the reduction process. We can find out all intermediate chemical species. Also, we can find out Gibbs free energy change. And we can apply also electrochemical potential as well. The onset potential for this chemical reaction is that when Gibbs free energy is become downhills. That potential is actually the spontaneous reaction happens, right? So we can capture that onset potential as well. But this is all about thermodynamic ground point of view. How about can you predict reaction velocity? Then you have to calculate the equation barrier. You can calculate. We can apply elastic band calculation, NEB calculations, and you can capture that actually activation barrier for certain reaction from the certain chemical to another chemicals. Very well captured, you can do. So this kind of formalism, all formalism can be computational framework to predict or discover or design certain materials. So you can incorporate this old methodology into certain one computational framework. That's what I'm doing these days. But now I'm doing also non-equal solution as well. The reason is that to separate spent nuclear fuel in the molten salt media. I'm from South Korea. We have a lot of discharge of spent nuclear fuels, but you don't have any solution for that unless deep underground at disposal. But spent nuclear fuel, we can still, there is a lot of unused uranium-based material, actinide. How about you can separate that material? Then you can selectively separate that one. You can utilize the gains. In that case, we are actually studying of the electrorefining step in the pyroprocessing technology. South Korea and the Idaho National Lab is cooperating of that project over the last 10 years. Now next year, project opens over next year. Probably we can make some like a pyro scale of devices to do electrorefining. I found out that in the uraniums, above tungsten electrode, the nucleation and the growth behavior is very different compared to vacuum condition and actually in the molten salt, chloride-based molten salt. You can see that nucleation and growth here. In vacuum condition, if you apply computations, then you can find out uranium can become very flat. But actually in the molten salt media, uranium cannot be like a flat layer biostructures, but they always grow in the dendrite form because of the green. Green is chlorine ions. Chlorine ion, uranium has very strong interaction between that. And then they just crank up uranium to grow in the dendrite formations. Of course, you know that the experimental observations show that uranium grow in the dendrite form, right? So it's very complete, agree with the experimental observation as well. I'm sorry. So these days we are working with a certain professor in the Korea and Albi Satov's in Lawrence Berkeley director, former director, to image out the in situ nanoparticle topology in the ligand basis. So this is really good. Why? We can model or discoordinate of nano atoms directly to the density functional theory calculations, and we can predict the topology generations, or the charge density plot. Also, we can apply analysis the strain if field on the particles. Then this is like really good to predict material property as well. This actually outcome is actually under review in the science paper. The other one I have done was that can you actually analyze the certain driving force for electrochemical reaction in the molten salt? We found out that europium 3+, europium 2+ are coexist in the molten salt media. But if you calculate uranium 3+, 2+ reaction, you're going to find out that enthalpy is non-spontaneous. There is it is endothermic reactions. But still you found out that uranium 3 plus and 2 plus coexist in the multimedia. So we analyze it by using thermodynamic ground, like Bantoff rho, and also the slope of a Gibbs reaction is like, with respect to temperature, is nothing but entropy. If you do apply these two equations, you're going to find out that this reaction is driven by entropy change, not by enthalpy change. To do that, we have to calculate it, the solvation shell structure, how tightly solvation shell form in uranium 3 plus and 2 plus. What is the Raman vibration spectroscopy? What is the diffusion coefficient of uranium 2 plus and 3 plus in the molten salt media? We found out that uranium 2 plus has much coarse solvation shell, and the diffusion coefficient is much higher in uranium 2 plus, which means uranium 2 plus is much higher entropy than uranium 3 plus. So this reaction is driven by entropy change. Recently, we also worked on published another paper in the IJELs. In Fukushima accident, we found out that core meltdown. In that case, we believe in that uranium and the zirconia, they react. And the zirconium ions replace uranium atoms, and they form corium type structure, corium complex actually. By computational calculations, actually, there is a possibility to do that. This is kind of a new field to predict structure in the completely inaccessible by experiments. But you still can predict that, right? This is the final topic I'm going to talk about. These days, we are studying of the stability of uranium, used uranium fuels when you dispose it in the underground. There is alpha decay. Whenever there is alpha decay by uranium, they form thorium with the helium gas phase. Helium gas phase, you know already, right? Nuclear engineering guys already know that. Or when the helium generated, is that uranium fuel still stable or not? So we found that we tried to calculate that the cell volumes of urea change as a function of thorium compositions. You see here the volume actually increases according to Vegard law, very well, a linear type of increasement of volume. But mixing enthalpy between uranium and thorium in chemical point of view actually is not really prefer each other, but you apply the entropy generations. Gibbs spray energy is slightly negative. So thorium and the uranium is okay. They do mix, yeah, but not so strongly. Then we calculated that can this structure, uranium, thoriums, and oxide, can incorporate helium gas phase thermodynamically. We found out that thermodynamically, helium is not stable in that lattice, very high instability of helium in that lattice. So something in the bulk phase is not maybe stable. You see here, diffusion of helium also not so feasible thermodynamically in the bulk of uranium. You see that uranium and oxygen, when the helium diffuse out, the bond length actually increased, but thorium and oxygen's bond length not changed, does not much change. Even though thorium is bigger than uranium, uranium and thorium has much higher enthalpy of formation than uranium and oxygen. So thorium form very rigid framework, so helium cannot diffuse out. Here we calculated activation barrier using NEB calculations. Activation barrier is very high actually. So we thought that probably helium just maybe go to just a grain boundary, not in the bulk phase. And we set up grain boundary models to estimate the energy of helium incorporations. We found out that 1 to 1 bulk phase can form grain boundaries. This grain boundary is much stable than two independent grains. Yeah, you see here, energy is much more favorable. And the incorporation energy here, depending on the location of the atoms, we found out that actually helium incorporation energy can be significantly decreased, which means the thermodynamically become very feasible to stay, which means at number two positions, helium may stay very well. This is actually the interface of the two bulk. Yeah. This is my end of story. I believe in that MIT plans to form a College of Artificial Intelligence by this September with 50 new faculty positions and the fellows more than 100 with $1 billion of budget. I think this is data center, right? Data center. Yeah. I think this is like really generate really this kind of methodology spread out all over the world. This MIT is always leading ecology in this field. Again, this is the target of machine learning technology, specifically in science and technology and sectors. Okay, thank you very much for my funding and your attentions and my group students. Thank you very much.